Okay, so welcome to the Math 53 practice final solutions video. And what I'm going to do is I'm going to solve the practice final slowly, explaining my thought process. And hopefully this will, give you an idea of how to approach problems that you may not necessarily immediately know how to solve, and also, clarify some of the concepts that are being tested. So if you have any questions, please just ask on Piazza. Let's start with the true false. So the first one is basic question about vectors. Their statement is there are two unit vectors u and v, so the sum has length a third. So the answer, so this is true. And the way to see this is to just think geometrically about what adding unit vectors means. So if I have a unit vector u and I add some vector v, well, I said that that means that you put the tail of v at the head of u and so on. Or I could also think of it as yeah, okay, so let's say I put v like this. And what I'm asking for now is I'm asking if there are vectors where u and v have length 1, so the sum u plus v, which is the third side of the triangle, has length a third. And so if I can construct a triangle with one side length equal to a third and two sides length equal to 1, then I'm done, because I can just take these vectors to be these sides of the triangle. And this is clearly possible. You can just take an isosceles triangle with base equal to a third. So this is true. And in general, if you ask about what lengths can you achieve when you add two unit vectors, well, it can really be anything between 0 and 2. And you can also see that from the formula for the length squared of the sum of unit vectors. So it's just this. And both of these norms are 1, so it's just 2 plus 2 times cosine theta, where theta is the angle between the vectors, and since theta can be anything between minus 1 and 1, this can be between 0 and 4, and so the square root will be between 0 and 2. Okay, so the second question, so if f is a continuous function, both the partial derivatives are defined and continuous on the plane, then the function must be differentiable on the plane. This is simply true. This is a theorem we stated in class in lecture 6. It's also stated in the textbook. It's just one of the basic facts about differentiation that we didn't actually prove, but we used repeatedly when we talked about functions. We often use this fact to just know that they were differentiable. Okay, so question C. The work done by a vector field on a particle moving along a curve C is independent of the time taken to traverse C and depends only on the trajectory. So you have this curve C, you have some particle moving along C, you have a vector field F. The question is, does the work done, mathematically, what's the work? It's just this line integral. Does this depend on how fast you move along C? If you move twice as fast, does the work change? Well, the answer is no, it doesn't change because the line integral is independent of parameterization. This is a fact we've been using, every day in the second half of the course. Like we talk about line integral along a boundary, and that's a well-defined thing. Doesn't matter which parameterization you use. So in particular, it doesn't matter if you go twice as fast, and so this statement is true. Okay. The number of critical points of a differentiable function in R2 must be finite. Okay. So before you start working on this, let's recall what a critical point is. So a critical point is just a point where of a function, let's say in two variables, is a point where both the partial derivatives are equal to 0. And so in order to cook up a function which has infinitely many critical points, I'd want the system to have infinitely many solutions. And we've seen many examples like this in class. The simplest one is just take f of xy equal to x squared. So then partial x is equal to 2x, is equal to 0 at a critical point, and partial y is just 0. So this is automatically equal to 0. So a set of critical points is just the set of points where x equals 0, and that's a line. That's infinitely many points. So this is false. Can easily have functions with infinitely many critical points. Okay, so part B is a slightly trickier question. So it says that if f is a solution of Laplace's equation, so Laplace's equation is a PDE that we looked at for the midterm, then the flux of the gradient of f through the unit sphere outwardly oriented has to be 0. Okay, so this seems kind of bewildering at the outset. It's saying if f solves some PDE, then the flux of the gradient, which is some concept that we encounter much later in the course, through some surface is 0. And so maybe the first thing to realize is to say, well, what does this PDE have to do with the gradient of f and the flux, right? So these are the clues. So what do I know? So this PDE has a bunch of second derivatives. So the first thing to observe is that the Laplacian, this is just equal to the divergence of the gradient of f. So it's equal to write it like this, it's more obvious. The gradient is just taking the first partial derivatives, and the divergence is then taking second partials and adding them. And so if something solves Laplace's equation, then I know that the divergence of its gradient is 0. In fact, that's exactly what it means. And now that I made this connection, this could be useful because I know the divergence of grad f is 0. But I want to compute its flux. Now, what theorems do I know? Do I know anything that relates divergence to flux? The answer is yes, the divergence theorem. So I know that the flux of f through the sphere S, which is flux of gradient of f through S, by the divergence theorem is just equal to the triple integral over the interior of S, so over the unit ball, so I'm going to call E, of the divergence of gradient of f. But hey, I just noticed the divergence of gradient of f is 0, so this has to be 0. So in fact, this is true. Okay, part F. F is a conservative vector field and its divergence is 0. Okay, so again, when you see a question, just write down what all the words mean, right? So what's a conservative vector field? Well, okay, so the dimension isn't specified here. So I could do 2 or 3 dimensions, but let's just check it in 2 dimensions first. So in R2, what do I know about conservative vector field in R2? Well, F is conservative if and only if its curl is 0. Which means that if F has components P and Q, Qx equals Py. So that's what conservative means. And divergence of F equals 0, what does that mean? Well, that means Qy plus Px equals 0. These are two very different, these are clearly different conditions on the vector field F, and the question is, does one imply the other? Well, it doesn't look like it, right? Once I have all these things on the table, I can just cook up an example where the curl is 0, but the divergence is not 0. So let's look at F equal to the vector field Qx equals Py. So let's see, let's do well, maybe the simplest thing is just to make both Qx and Py 0. So let's just look at the vector field components x and y. Then you have that the curl of F is 0. So Qx minus Py is 0 because Qx is 0 and Py is 0. But the divergence of F is 1 plus 1, which is 2, which is not equal to 0. So that this is false. You can have a conservative vector field with non-zero divergence. Okay, two more questions on divergence and curl. There exists a vector field f, so the divergence is equal to x squared plus y squared plus z squared. So since the divergence is a function of three variables, we assume the vector field on R3. And again, let's just write down what the quantities mean. So divergence of f is just pxx. Px plus qy plus rz if f is equal as component q of r. So again, when you want to come up with examples, just write down the components. It'll help you search the space of examples. And so I just want to cook up an example so that this is equal to x squared plus y squared plus z squared. That's pretty easy. I just want to find p, q, and r so their derivatives add up to x squared plus y squared plus z squared. An easy possibility is that f be, in this case, x cubed by 3. So if you differentiate this, you will just get x squared, y cubed by 3, and z cubed by 3. And then the divergence of this is indeed equal to what's desired. This is true. Problem H, there exists a vector field so that curl is equal to x squared, y squared, z squared. Okay, so what is curl? So again, let's say f is equal to p r. Now what's the curl of a vector field in three dimensions? Well, it's its determinant, right? Okay, it's a vector. It seems a little bit annoying to compute, to check whether I can find some f so that, this vector is equal to x squared plus y squared, x squared, y squared, and z squared. That sounds kind of tedious. So maybe before plunging into that, so again, if you find anything tedious on the exam, before wasting a lot of time on it, just think about, is there some conceptual reason why is there a conceptual solution? Is there a conceptual reason why this is impossible? So let's think about what we know about curl. Well, I mean, one of the things about curl is that divergence of curl of any vector field is equal to 0. And maybe we can check, does this rule out the possibility that you have some vector field with curl equal to this specific field? So let's compute it. So on the other hand, divergence of given field is just 2x plus 2y plus 2z. And divergence of curl is 0. It has to be 0 everywhere, right? That's a fact that's true everywhere. And this is not 0 everywhere. Okay, so in fact, this is not identically 0, so there is no such vector. So the answer to part H is false. And again, I mentioned this fact. I mentioned this fact a few lectures ago. There's an algebraic proof, but I also mentioned it in the last lecture. This follows from Stokes' theorem. Okay, last two true false. So if you have this vector field f, which has constant components, a third, a third, a third, then the flux across any oriented surface cannot be larger than its surface area. So again, what's the flux? Flux is a surface integral. So it's the integral with respect to surface area of the normal component of the vector field. Now, the claim is that this thing is at most the surface area. Okay, so let's write down what the surface area is. Again, the general principle, always write down the meanings of all the words. Surface area is just the integral of 1 ds. Now, certainly the flux would be smaller than the surface area if this integrand is always at most 1, right? So is it true that this thing is always at most 1? Well, let's think about it. So n is a normal vector. It's a unit vector. And f is this vector that's fixed, okay? And what's the norm of f? So, I mean, how big is f, right? So we want to get an upper bound on this dot product. Certainly, if both the vectors are unit vectors are smaller, this cannot be bigger than 1. What's the magnitude of f? It's square root 1 over 9 plus 1 over 9, which is 1 over square root 3, which is certainly less than 1. So in particular, I know that this dot product that shows up in the flux integral, it's equal to magnitude of f, magnitude of n, cosine times the angle between them. So it has to be less than 1 over square root 3. And so in particular, this flux, this is true. So it's less than 1. In fact, it's less than 1 over square root 3. So actually, yeah, the flux is always less than or equal to 6. This was a little tricky because it required you to, combine a few different concepts. Like think about what the flux means geometrically as this dot product, and then reason about the dot product using the lengths of the vector. Okay. Now for the last one, the flux of the vector field F in 2 dimensions with components P, Q. So if this flux is 0, then F has to be conservative. Okay. Okay, so again, there's a lot of moving parts. Let's write down what everything means. So there's the flux of the vector field across a closed curve. So the picture is some closed curve in the plane. And I'm interested in computing the flux. So that's the integral of the normal component across this plane. And I'm told that this is 0 for every curve. Okay. I mean, before proceeding, you can ask, does this tell me, I mean, this is sort of a maybe unwieldy statement. Does this tell me anything else? Does this give me any other interesting information about f? And the answer is yes, it actually tells me something about the divergence of f. So by the divergence theorem, this flux across every closed curve is actually the area integral of the divergence. And if this is 0 for every curve, the divergence of f actually has to be 0. This is something we said in the last lecture, but in any case, for the purpose of this true-false statement, certainly, so in fact this is an if and only if, but certainly we know that if the divergence is 0, then the flux is 0 by Green's theorem, okay? So in order to contradict this, we just need to come up with a function whose divergence is 0, which is not conservative. Okay, so again, what does it mean to be conservative? So conservative if and only if the curl is 0, the curl of f is 0. Okay, so now we just decoded what all the words in this question mean. So it's asking, if I give you a curve where the divergence is 0, does the curl have to necessarily be 0? This is what the question is asking. This is actually sort of the converse of a true-false question maybe 2 or 3 questions ago. So if I know the divergence is 0, does that mean the curl is 0? Well, I mean, definitely not, right? Think about what divergence means. Divergence means that there's no sources or sinks. So for example, consider the vector field that's rotating counterclockwise. So this is a vector field with components y, x. So this component, the divergence is 0, but the curl, which is qx minus py, is minus 2. Okay. So actually, okay, this should be going in the opposite direction. Right. Mess this up. Okay. But in any case, we now have a vector field whose divergence is 0. So by Green's theorem, the flux is 0 across every curve, but the curl is not 0, so it's not conservative. So this is also false. Okay. So in this problem, we have a particle moving along the intersection of 2 surfaces given by these equations. So the intersection of two-dimensional surfaces in 3D is a one-dimensional curve. And we're given that, there's some parameterization x, y, z of t of this curve. And we know the position of the curve at time 0, and we're told that the x velocity at time 0 is 1, and we have to calculate the y and z velocities. Okay. So there are a number of ways to solve this problem. What's the most obvious way? So here's the most obvious way. Method 1 is actually find a parameterization, find an explicit parameterization of the intersection of these two surfaces by, maybe solving these two equations. They don't look that fun to solve, and actually the solution is not very pretty, but you could in principle do it, and then, match up, the velocity at 0 to be 1. That's the normalization we're given. Remember, there are many parameterizations of this curve. And then given that, use this to find, y prime 0 and z prime 0. So this is a valid method. It's sort of annoying because finding the parameterization is hard, right? In this case, for example, what happens if you plug the second equation into the first one? You get x squared plus y squared plus 2x squared y squared equals 4. And you will get some parameterization, but this is annoying. What I'm going to do is show you two slicker methods. First, method 2. And the key observation is the problem doesn't actually ask us to find the parameterization, right? It doesn't ask us to find the whole parameterization. So can we somehow get away with, finding less information? And so the clue is that, well, we're only interested in the velocity at a specific point, okay? And so that's very local information. And so, we should in principle be able to compute that just by looking at what's going on around this point 1, 1, 1, instead of computing the whole parameterization. Let's draw a picture. So what's going on here? So there are these two surfaces. So one is the surface, I'm going to call this g of x, y, z equal x squared plus y squared plus 2z equals 4, given by the first equation. And then there's some second surface. It's not a very good picture. Again, I'm going to write this as a level set. I'm going to say this is h of x, y, z equal to z minus x, y equal to 0. It's supposed to be a 0. And there's some point 1, 1, 1 at the intersection of these things. And I want to find, so these things intersect in some curve. And what I'm interested in is, I want to find the tangent vector to that curve at that point. Because if I can do that, then, I can figure out the y and z partial derivatives, which are just coefficients of the tangent vector, using the value of the x derivative. So goal is to compute a tangent vector at 1, 1, 1 to the curve of the intersection of these two. Okay, so what's the geometric strategy? Well, this tangent vector lies in both of the tangent planes. So it lies in the, so what's the observation? The observation is that this vector lies in tangent planes to both g equals 4 and h equals 0. Okay, and so if I can find both of those tangent planes, then maybe I can use that to find the tangent vector, and that's exactly what I'm going to do. So how do we find tangent planes? Well, the surfaces are given as level sets, and so the tangent planes, the normals are just given by the gradient. So find the normals to the tangent planes, which are, to both surfaces. These are given by the gradient. So the gradient of g in this case is just going to be 2x, 2y, 4z. And the gradient of h is going to be, in this case, minus y minus x. And at the point we're interested in, this is equal to just 2, 2, 4. This is equal to minus 1, minus 1, 1 at the point that we're interested in. Okay, so now we found roles about these tangent planes. And so the tangent vector, the line at the intersection of these two planes, so the tangent vector is the velocity at this point, is going to be perpendicular to both these normals. At the point. And so in particular, it means I can find it using a cross product. So if I take v equal to the cross product, then I will get a tangent vector to the curve at that point. So let's just calculate this. So this is I. I'm going to get 2 plus 4 minus j 4 plus k uh, 2 plus 4 as well. No, I'm sorry. I've this wrong. What am I doing? K is just minus 2 plus 2. So it's just a vector of 6i plus 6k. So that means that a tangent vector to the line at a point is just 6i plus 6j. I'm sorry, 6i minus 6j. And so what does that mean? So I know that if I have any parameterization of this curve, this has to be parallel to this tangent vector. So it's equal to some constant times 6 minus 0 at that point. And if you solve this, since we know that this is equal to x prime naught is equal to 1, we get that c is equal to a sixth, which implies that y prime naught is equal to minus 1, and c prime naught is equal to 0. And that's the answer. Okay, so the point of this was we managed to find these derivatives at this point without actually calculating the parameterization. All we needed was local information, and all that information was contained in the gradients and tangent planes. Okay, so I just want to remark, by the way, that there is a third method of doing this, which will give the same answer. So let me just put it here. Method 3 to use total differential. So I mean, under the hood, it contains the same information. Total differentials. Remember, the total differential of a function is this shorthand notation for the linear approximation, which essentially encodes the same information as a gradient. It tells you what the tangent plane is. But I could use total differentials to reason about the tangent planes to find the equation of the line in both the tangent planes. So again, what's the total differential of g in this case? So this is going to be 2x dx plus 2y dy 4z dz 0. And total differential of h, again, since both of these things are level sets, these differentials are 0. This is going to be just dz minus y dx minus x dy equals 0. Okay. So these, they describe linear approximation at any point, but in particular, at the point of interest, they'll define both the linear approximations. And the linear approximations are just graphs of the tangent planes. And so, you want to think of these as just a shorthand notation for the equations of the tangent planes centered at the point 1, 1, 1, the point of interest. Okay. So we're interested in the line at the intersection of both these planes. How do we find this line? Well, we just solve these equations. So, or even we don't even necessarily want the equation. We just want the relationship between the change in y for a particular change in x, right? We want to find y not 0 given x not 0 and z not 0 given x not 0. So actually all we want to do is express dz and dy in terms of dx. And we could do that by solving these equations. So again, at the point 1, 1, 1, this becomes 2dx plus 2dy plus 4dz 0. Second equation is just dz equals dx dy. So now if you plug the first equation to the second one, you get 2dx plus 2dy plus 4dx plus 4dy equals 0, which implies dy equals minus dx. And now if you plug this back into the third equation, you get dz equals dx minus dx equals 0. And so indeed, you get the same answer as you got in the previous one. So what this implies is that since x prime not equals 1, we know that y prime not equals minus 1, z prime not equals 0. Same answer as we got by the other method. Okay, so this is a question about directional derivatives. So we're given a function f, and we're told that its directional derivatives in these two funny-looking directions are as shown here. And there are two parts. In the first part, we have to use this information to find the partial derivatives. Let's do that first. So again, what does directional derivative mean? Well, directional derivative in this direction, 1 over root 2, 1 over root 2 of f, well, it's just a particular linear combination of partial derivatives, right? So it's the derivative when you move in this direction, but as we derived in class using the chain rule, this is just equal to 1 over root 2 fx plus 1 over root 2 fy. And so what we're given is that this quantity is equal to square root 2 x. So let's call that equation 1. Similarly, we know the directional derivative in this other direction, which again is just a linear combination of partial derivatives, is equal to square root 2 y. Let's call that equation 2. And now given this, our goal is to find fx and fy. So as you can see, this is just a system of linear equations, two unknowns. The only difference between what we may have done before is that the unknowns are functions. The unknowns are these functions fx and fy. But you can still do the same thing. So in this case, it's particularly easy if you add the two equations. Then what do you get? The fy's cancel. You get 2 over square root 2 x equals square root 2 x plus y. And now you have a square root 2 on both sides, which cancels, so you get fx equals x plus y. And for the second part, you can just sort of eyeball it. If you subtract the second equation from 1 minus 2, then you get 2 over square root 2 fy equals square root 2 minus y, and so fy equals x minus y. Okay, so that was pretty easy. Now in the second part, you have to use this information. So what did we learn in the first part? We learned that fx equals plus y and fy equals minus y. And now the goal is to actually find the function given these derivatives. And we're given one more piece of information that at 0, the function is 0. So this is something we've done in the class, maybe in a slightly different context. We've done this in the context of finding a potential given a conservative vector field, but it's the same thing. You have a hidden function f, and you know its partial derivative, and you want to find f. So the technique is again partial integration. Integrate with respect to x first, and then with respect to y, or whichever order you want. But let's just do x first. So let's integrate this partial in x with respect to x. So what do I get if I do that? Well, I get that is the integral of x plus y dx, which is x squared over 2 plus xy plus any function g of y. Okay, so actually what I've concluded is that f has this form. Function f must be equal to x squared over 2 plus xy plus some g of y. And the reason it's g of y and not a constant is that we only integrate with respect to dx. And so since differentiating an x kills any function of y, we have to add this function gy instead of just a constant. So now, how do we find out gy is? Well, we plug this back into the other equation. So what happens when you plug this back into partial f with respect to y equals x minus y? Well, let's differentiate this in y. G of y. So everything, the first term just goes away. The second term becomes x plus g prime y. And we know that this equals x minus y. So therefore, it must be that g prime y equals minus y. And then we can just integrate this in y, which implies that gy equals minus y squared over 2c. So that's it. We solved the problem. Combining all this information, we get that f of y must be equal to x squared over 2 plus xy minus y squared over 2 plus a constant. And the constant, we don't know what it is, but now we finally use this information that at 0, this is 0. And so if you plug in x and y equals 0, you get that c equals 0. And so, so actually the function is just squared over 2 plus xy minus y 2. And you can, you can now, just for sanity check, you can check that the partial derivative of this with respect to x is x plus y, and the partial derivative with respect to y is x minus y. Okay, so in this question, we're given that x, y, and z are constrained by some equation, g of x, y, z equals 3. We're not even told what g is, and like what the function g is, and we're told that at the origin, the value of g is 3, and the gradient is some specified vector. So implicitly, g equals 3, this is a level set. This defines a surface in R3. We're told that the origin is on the surface, and we're told that the gradient, which is a normal vector to the surface at this point, is 2 minus 1 minus 1. And using this information, we're asked to find what's partial z partial x. Since, given one equation and 3 variables, this implicitly defines z as a function of x and y. Right? If I fix values of x and y in a neighborhood of the origin, it will give me a value of z. At least that's what I'm told. Okay, so how do I find partial z partial x? So there are, again, a couple of methods to do this that are related. So method 1 is to study the linear approximation at the point. So the linear approximation is the function whose graph is the tangent plane. And the whole point of calculus is that, well, taking derivatives, allows you to approximate the value of a function near a point, because every function, if you zoom in, looks flat. And so let's figure out what the linear approximation at the origin is. So so this information is contained in the gradient. So what do I know about the linear approximation at the origin? Well, suppose I know the value at the origin is just 3. But what's the value at a point near the origin? So delta x by delta z. Well, it's about equal to the linear approximation, which is value at the origin plus the partial derivative in x times delta x plus dy delta y plus dz delta z. So in particular, the change in the value of g is about, so that's moving the 3 over to the other side, is about gx delta x, gy delta y, gz delta z, and I know what gx, gy, and gz are because I know the gradient. So this is about 2 delta x minus delta y minus delta z. But wait a minute, I'm staying on the surface. So actually the change in z should be equal to 0, right? So if z is a function of x and y such that g stays at a fixed value, then delta g is 0. So now I have this relationship between delta x, delta y, and delta z, that 2 delta x minus delta y minus delta z is very close to 0. And now I can think about the partial derivative. So the partial derivative is asking what's the rate of change of z with respect to x if y is kept fixed. So to compute partial z partial x, I'm going to set delta y equal to 0. And then I get that 2 delta x minus delta z is about 0, which is the same thing as saying that delta z over delta x is close to 2. And so if you take a limit of this, you get that partial z x is equal. Okay. So we were able to read off this information just by looking at the linear approximation. Geometrically, what's going on here is I'm just looking at this tangent plane. And I'm asking, so this is a plane. What does partial z partial x mean? Well, it means if I look at the trace inside this plane, with the line y equals 0, so there's a plane centered at the origin. If I set delta y equal to 0, that amounts to saying I'm just going to look at the slice of this plane in the xz plane, which is a line. I'm going to compute the slope of that line. The slope of that line is 2. Okay, here's a second method for doing this. That's a little slicker, but ultimately means the same. This is just total differential. And you'll see how this is really packaging the same information in a different way. So what do I know? I know that g equals 3 on the surface. And so in particular, I know that the total differential of g, which is of this form, the total differential has to be 0 because the value of the function doesn't change. And then the total differential is just again, the coefficients are given by the gradient, so 2 dx minus dy minus dz. And now, so this is the relationship between dx, dy, and dz. And now I'm interested in computing partial z, partial x. So I set dy equal to 0 because I'm fixing the y variable. I get 2 dx equals dz. So quantity I'm interested in. Okay, so this is really, you can see it's the same calculation, it's just different notation. It's in some ways slicker, and if you're comfortable with it, you can do these problems more quickly. And that's why we have the shorthand notation, because this comes up so often. Okay, so in this question, there's 3 parts. We're asked to do a bunch of things. So in the first part, we're asked to find the equation of a tangent plane to a surface that's given as a level set of some function. So in part A, the surface S is given as a level set of g of x, y, z equals 0, where g is the function 4xy minus c. So to find a tangent plane, we need 2 things. We need a normal vector and a point. We already have the point. We're told to find a tangent plane at this point 1, 1, 2. So all we need to do is find the normal vector. And the fact that we've used many times already that we're going to use again is that the normal vector to a level surface at a point is given by the gradient. So the gradient of g is the vector. So again, the entries are just the partial derivatives with respect to x, y, and z. So you get 4y, 4x, and minus 2z. And this is the gradient vector at any point, but at this particular point, 1, 1, 2, just going to plug in 1, 1, 2, it's 4, 4, minus 4, p. So we computed the gradient vector at P, and this is normal to the surface. So if I want to find the tangent plane, this is a normal vector that I can use. So the easiest thing to do is to just use these two ingredients and go back to the equation of the plane. So tangent plane has an equation, the normal vector, which is 4, 4, minus 4, dot position vector of an arbitrary point on the plane minus specific point, which is 1, 2, 0. And if you want to convert this in terms of x, y, and z, well, you just, a position vector, if that has coordinates x, y, and z, then what would this become? This would become 4 x plus 4y minus 4z. That's the dot product of the first entry, minus the dot product of these two vectors, which would be 4 plus 4 minus 8 equals 0, which if you simplify it, you will get something of the form ax plus by plus cz equals d. So I guess, well, actually, in this case, I guess 4 plus 4 minus 8 is just 0. So actually, the equation of the tangent plane is just 4x plus 4y plus 4z equals 0. Okay. Okay, so in part B, we're told to use what we did in part A to approximate the value of some number, which is actually just an evaluation of g at a point that's very close to the point P, but not quite. So this is at the point 1 plus 0.001, 1 minus 0.01, and 2 plus 0.001. Okay, so in part B, we're asked to find an approximation to this quantity. And so, the way to proceed is to say, well, it's pretty similar to g evaluated at 1, 1, 2, which is easy, except now we've perturbed the inputs by these tiny quantities, delta x, delta y, and delta z. And the linear approximation of g at this point P is given by what we just calculated, the tangent plane. So this is about g at 1, 1, 2 plus delta x. Now partial x is given by the gradient. So we did just calculate the gradient, right? It's 4, 4 minus 4, so plus 4 delta x plus 4 delta y minus 4 delta z. And so now we just plug this in. So G112 is easy, so that's 4 times 1, that's just 4, minus 2 squared, which is 4, so that's 0, plus 4 times delta x is 0.001, plus 4 times delta y, which is minus 0.01, plus, minus 4 times 0.001. And so, well, okay, these 0.001s actually cancel out. There's a plus 4 and minus 4, so all you're left with is just it's minus 0.04. Okay. And finally, in part C, it's asking find the equation of the parameter equation of the line through P perpendicular to S of P. And again, what's the picture? There's some surface, there's point P. We just calculated the tangent plane at this point. It had a normal vector, which was given by the gradient. And well, okay, so if we want the line perpendicular to S, that's going to be parallel to the gradient. It's going to be parallel to the normal vector of the plane. So the line goes through point P, which has coordinates 1, 1, 2, and is parallel to the gradient of G at this point 1, 1, 2, which we calculated and it's used many times as 4, 4 minus 4. And so the parametric equation of a line like that is just R equals 1, 1, 2 plus P times 4, 4. Okay, so that was quite straightforward. Okay, so this is a question about Lagrange multipliers. You want to find a point on some surface where some function is maximized. So in this case, I mean, we could just start writing down the equations and solving them, but let's draw a picture. The surface is fairly simple. You'll write, I mean, if there's no 5, 1, and 3, it would just be a sphere, but with these coefficients, it's just an ellipsoid. So surface is, I don't know, some sort of an ellipsoid. This is the surface G equals 9. This function is a linear function. I don't know, I'm not drawing it precisely, but its level sets are planes. And so what we're looking for is, it has a lot of level sets. We're looking for like this point right at the edge. We're looking for the largest value of f at which the level set intersects my constraint set. So this is level set of f. Okay, so again, Lagrange multiplier is based on the idea that at this magic point, what happens is that the gradients of both the constraint function and the objective function are parallel. So Lagrange multiplier equations, what they tell us is that at the optimum, following two things happen. So the gradient of g is parallel to the gradient of f, and g is equal to 9. I mean, that's just given. So now let's just compute these things and solve these to find some candidates for what this point is. We don't know a priori that there's only one, but let's just write down the equation. The gradient of g is pretty straightforward. So differentiate this in x, you get 10x. Differentiate in y, you get 2y. Differentiate in z, you get 6z. Gradient of f is even simpler. The constant term doesn't matter. You just get 5 plus 2. And so the equations tell us that at the optimum, 10x 2y 6z is equal to some constant times 5 minus 2 9, which immediately tells us that we can express the points in terms of this one constant c. So x must be equal to 5c over 10, which is just c over 2. Y must be equal to minus 2c over 2, which is minus c, and z must be equal to 9c over 6, which is 3/2 c. Okay, that doesn't solve the problem because we don't know what c is, and this is where we use the second equation. So if we now plug this into g equals 9, we get that c over 2, we get 5c over 2 squared plus c squared plus 3 times 3c over 2 squared equals 9. And if we expand this out, then what do you get? You get 5c squared plus 4c squared plus 27c squared over 4 equals 9. And okay, 5c squared plus 4c squared plus 27c squared is 36c squared. So we get 36c squared equals 9 equals 36. So c equals plus or minus 1. Gives me two candidates. It actually gives me 2 points, which could be the optimizers. So now it asked me to find the maximum. So I have to check whether, which one of these is the maximum. Both of them are. And intuitively, what I expect is one of them is going to be the minimum, one is going to be the maximum, right? So one's going to come from the minimum, which is directly on the opposite side of the ellipsoid, and one's going to be the maximum. I just have to check which. And to figure out which one's the maximum, I just have to evaluate the function. So my candidate points, I have 2 candidate points. I have the points are plus or minus a half. Oops, sorry. Plus or minus a half, minus 1 and 3 over 2. And so there are 2 points, and now I'm just going to check the value of the function at each point. So f at a half minus 1 and 3 halves is equal to 750 plus 5 over 2 minus plus 2 plus 9 and 3 over 2. And f at the other point is equal to 750 minus, so I just flip all the signs, minus 5 over 2 minus 2 minus 9 times 3 over 2. And clearly the top one is, this is bigger, right? Because it's a bunch of positive numbers, and at the bottom one I just reduced, I just flipped the signs of some of them to make it small. And so this one must be the maximum. And so, you know, it just asked me to find the point where it's maximized, not the maximum value. So I don't even have to add these things up. So the maximum is achieved, or I'm sorry, this one should be minus. So the maximum is achieved at point a half minus 1, 3 half. Okay, so in this question, we have to classify the critical points of some function using the second derivative test. Okay, so remember the critical points. So what are critical points? They're points where the gradient is 0. So both the second derivatives are 0. So before we classify the critical points, we have to find them. So to find critical points, we have to solve 2 equations, namely the partial derivative in x is 0 and the partial derivative in y is 0. So what's the partial derivative in x? Well, only the first 2 terms matter. You get 51x to the 50 minus 51 equals 0. And that has a solution x to the 50 equals 1, which means x equals plus or minus 1. And now, so, okay, so that gives us, narrows down the search. It means that the critical points are contained in these 2 lines, x equals 1 and x equals minus 1. And now we do the same for y. For y, we get partial is minus 51 y to the 50 plus 51 equals 0, which again has a solution y equals plus. So to be a critical point, both of these things need to happen. So the critical points are x equals plus or minus 1 and y equals plus or minus 1. So there are 4 critical points. Okay. So to classify them, remember what's the second derivative test? Second derivative test, you know, determines whether, well, sometimes determines whether a critical point is a local maximum, local minimum, or saddle point, depending on this determinant. And so to calculate this, we need to figure out what these second derivatives are, and mixed derivatives as well. So let's do that. So fxx is, I'm just going to differentiate fx again, and I'm going to get 51 times 50 x to the 49. Fyy is going to be minus 51 times 50 times y to the 49. And fxy is just 0 because fx doesn't have any y in it. Okay. And so in particular, what that means is that this quantity I'm interested in is just going to be the determinant of 51 times 50 x to the 49, 0, 0, minus 51 times 50 y to the 49, which is just 51 times 50 squared with a negative sign because the second thing is minus x to the 49 y to the 49. So that's what this determinant of this 2 by 2 matrix, the Hessian, is at any point actually. And so now we have 4 critical points. We have 1, 1, 1, minus 1, minus 1, 1, and minus 1, minus 1. And at each point, we can calculate the value of d according to this formula that we derived. So what's the pattern? Well, x to the 49, if you plug in +1, it's positive. If you plug in -1, it's negative. And so this quantity generally, at any point, is going to be -1 if x and y have the same sign, and +1 otherwise. So it's going to be -1, or not -1, -51, -51 times 50 the whole squared, but in any case negative, positive, um, positive, and negative. And so in particular, this tells us the type of critical point. So remember that when d is negative, it's a saddle point. When d is positive, it's either a local maximum or a local minimum. And which one it is depends on the signs of the two derivatives. So if it's positive, it just means that fxx and fyy have the same sign. And so at the point 1, -1, they're both positive, and so it's actually a local minimum. Again, it's a saddle, negative, and at the point, I'm sorry, again, it's a local maximum. At the point -1, 1, because at that point fxx is negative and fyy is also negative. And at the point -1, -1, it's again a saddle. Okay, so that classifies the critical points, and we're done. So notice that in this case, I actually derived a formula for d at an arbitrary point xy. That's just because in this case, it was easy to calculate the determinant. In general, you could also calculate d separately for each point just by plugging in the numbers. But since I knew it was going to be a little bit quicker this way, I did it this way. Okay, so it's our first integration question. And it's just a simple iterated double integral. So it's saying, hey, okay, there's this integral, evaluate this by changing the order of integration. So before I do that, let me explain how this could come up in practice. So notice that if I just want to integrate this as is, the inner integral is an integral in y. And that would mean I have to integrate e to the minus y squared, and that doesn't have an antiderivative. So it's actually impossible to evaluate this in the order given. So it goes to switch the order of integration. So again, I mean, the right thing to do is think about what region of integration this defines. The two inequalities here are that x is between 0 and 3, and y is between x squared and 9. This is a classic type 1 region. Let's just draw it in the plane. So x and y. So x goes between 0 and 3. And now y goes between x squared and 9. So there's a curve y equals x squared like this. And the region we're interested in is this right here. And this point is a point 3, okay? That's a type 1 region. Now, if we want to turn this into a dx dy integral, which is, in other words, type 2 region, we want to think about expressing this as a range of y and then a range of x given y. So what's the range of y? This picture? Well, you can clearly see it goes from 0 to 9. So y is less than 0, y is greater than 0 and less than 9. And now what's the range of x given y? So that corresponds to asking, if I fix a horizontal line here, what's the range of x that I see? Well, it starts at 0 and it goes until this curve, y equals x squared. So x is at least 0, and at most the point on this curve, y equals x squared. And if y equals x squared, then x equals square root. So the integral, so that gives me an expression of this as a type 2 region. So the integral is equal to the integral from 0 to 9, 0 to square root y, the same function, x times e to the minus y squared, dx dy. And this is going to make my life a lot easier because now I can do the inner integral easily. It's just, as a function of x, it's just x times a constant. becomes integral from 0 to 9 x squared over 2 e to the minus y squared. Now the limits are square root y to 0. And so, okay, the 0 term just goes away. I just get integral from 0 to 9 y over 2 e to the minus y squared dy. And this I can do by, I could either see that it's a derivative or something, or I could do by simple u substitution. So let me take u equal to y squared. By the way, now you probably realize that u substitution is just a one-dimensional case of change of variables. We've been doing in this course as well. So u equals y squared, du equals 2y dy. This is the change of variables. So once I plug this in, the limits go to 0 to 81. Y dy becomes du, the half remains, so I get 1 over 4. I get a half from before and a half from the change of variables, e to the minus u du. And that's easy. That's a quarter times minus e to the minus u, evaluate 81 and 0, which is 1 minus e to the minus 81 divided by 4. Okay, so this was, again, the key is to maybe draw the region, write down the inequalities, and ask yourself these kinds of questions to figure out how to describe the region in this different order. And again, it's important to look at the boundary. Like here, the curve y equals x squared was really important to understand that that gives the